Welcome to day 6. You've got your homework there. Next class, we will be doing an intermediate day, day 6.5, where we'll do a bit of a discovery activity. So because of that, this homework, day 6, is not due until 2 class periods from now. Because next class we'll do day 6.5, we'll call it, and then the next class after that we'll do day 7. Okay, so this homework is not due until 2 class periods from now. So you've got your homework answers there. We'll pause for 2 minutes for you to check those. There's some more homework answers for you. We'll pause for 2 minutes to check those. And like usual, we'll pause on the work.solutions just for a second. If you need the sub to stop on any of those, just shout out for the sub to pause it. When you're good, let the sub know that they can restart the video. So we'll pause on each of the slides for about 5 seconds. Remember, just shout out if you need the sub to stop on any of those so you can see the worked out solutions. Let them know when to keep going. All right, so the sub should be passing out a sheet of graph paper to each of you. So on that sheet of graph paper, I want you to start out by making the t-table that is shown there. And what we want to do is we're going to do the x values just so everyone's doing the same thing and it's easier to organize this through a video. Let's do -1, 0, 1, and 2 for the x values. And I'm going to pause the video for 2 minutes. I want you to have the y values filled in and the derivative values at each of those values of x. So we should have had y values of 1, 0, or sorry, 1, 3, 5, and 7. Sorry. And then our slope values, because it's linear, the derivative should just be a constant. It was always 2. So next we're going to find the inverse. So I'm going to scroll down a little bit just so I have some room. So in inverse, you always switch the x and the y, and then get y by itself. So in this case, we're going to have x equals 2y plus 3. And then we get y alone. So we'll subtract the 3 over to get x minus 3 equals 2y. And if we divide everything by 2, we'll have 1/2 x minus 3/2 equals y. And then what we're going to do is we're going to make a similar table for the inverse. And I'm missing my equals here. And I think when you guys did these back in Algebra 2, after you got the y by itself, I think your Algebra 2 teachers wrote like the -1 there to signify inverse. So we're going to make a similar table for this. We're going to have x. These are our y values of the inverse. And then we're going to find the derivative at each of those points. Well, we're going to use the same points as we did before. So we had -1, 1. In an inverse, you switch the x and y. So we're going to have 1, -1. Then we had 0, 3. So when we switch that, we'll have 3, 0. 1, 5 will become 5, 1. And 2, 7 will become 7, 2. Well, because our inverse is linear, its derivative at every point is the same value. So we should get 1/2 for each of those. So what we're going to be doing, we're going to do 3 examples like this, and our goal is to come up with a rule about derivatives of inverses. So I want you to just look and compare our derivative columns for a second. And in your head, see if you can make any conjectures. Conjecture is a prediction that you think to be true. All right, so we're going to go on to a second example now. I was going to have you graph these, but just in the instance of time, really all we would notice on the graph is that it's reflecting over y equals x, those two graphs. So we're going to do the same thing for x cubed plus 2. So this time, I'm going to have you use 5 points. So let's do at -2. Let's do -1, 0, 1, and 2. And we're going to pause for 2 minutes again. I want you to find your y values for x cubed plus 2 and your derivative values at each of those points. So we'll go ahead and pause for 2 minutes to give you a chance to do that. Well, we should have gotten -6, 1, 2, 3, and 10. Our derivative of this is 3x squared. So when we sub in those values of x, we should have gotten 12, 3, 0, 3, and 12. So we're going to go ahead and take the inverse. So I'm going to scroll down just so we have some room. So our inverse will switch x and y. So we'll have x equals y cubed plus 2. And then we'll work to get y by itself. So we'll subtract 2 on both sides. And then when we take the cubed root of both sides, we'll have cubed root of x minus 2 is equal to y. And then in Algebra 2, you guys usually called it y inverse then, just to be clear that it wasn't the same as y. So we're going to make a chart. For this one, we'll have x, we'll have y inverse. I'm still going to write it as dy dx, even though it's really dy inverse dx. Hopefully we get what we're doing there. We're just taking the derivative of the inverse. And our points we had before, we had -2, -6, so now that's going to be -6, -2. We had -1, 1, so that's going to be 1, -1. We had 0, 2, so that's going to be 2, 0. We had 1, 3, so that's going to be 3, 1. And we had 2, 10, so we'll have 10, 2 now. So for dy over dx, well, we need to find our derivative. 1/3 would come out front. X minus 2 will now be raised to the -2/3 times the derivative of the inside, which is just 1. So this is really 1 over 3 cubed root of x minus 2 squared. So if we sub in our values of x, -6 minus 2 is -8. Negative 8 squared is 64. Cubed root of 64 is 4. 4 times 3 is 12. So we get 1/12 for this first derivative. If we sub in x equals 1, 1 minus 2 is negative 1. Negative 1 squared is 1. Cubed root of 1 is 1. 1 times 3 is 3, so we have 1/3. Next one, when we sub in 2 for x, we get 0 in that cubed root, so we're going to have 1/0, so that's just undefined. When we sub in 3, 3 minus 2 is 1. 1 squared is 1. Cubed root of 1 is 1. Times 3 is 3, so we'll have 1/3. And then when we sub in the 10, 10 minus 2 is 8. 8 squared is 64. Cubed root of 64 is 4. 4 times 3 is 12, so we get 1/12. So I want you to make a conjecture. What do you notice about your slopes of the inverse compared to the slopes of our original? And note these are at their corresponding points. When we flip the x's and y's, at their corresponding points in the inverse. So we're going to do one more example, see if we can hammer it home. So this time we're going to look at square root of x minus 3. So you can either write that on the bottom or on the next page. So what we're going to do here is we're going to use x values that will yield nice y values. So we're going to use 3, 4, 7, and 12. And we're going to give you 2 minutes. We're going to pause the video and allow you to find the y's and the derivative values. So we should have square root of 0 for the 3, so that's 0. Square root of 1 for the 4 is 1. Square root of 4 for the 7 is 2. And we'd have square root of 9, which is 3 for the 12. So our derivative should have been 1/2 x minus 3 to the negative 1/2 times 1. Well, that's the same as 1/2 square root of x minus 3. Well, when you sub in 3, you get a 0 in the denominator, so this is undefined. When you sub in 4, you'll get 4 minus 3 is 1. Square root of 1 is 1. 1 times 2 is 2, so we'll get a 1/2. When you sub in 7, 7 minus 3 is 4. Square root of 4 is 2. 2 times 2 is 4, so we'll get 1/4. And then when we sub in 12, 12 minus 3 is 9. Square root of 9 is 3. 2 times 3 is 6, so we'll get 1/6. So now we want to do the same thing for the inverse. I'm going to go down here so we have some space. And let's find the inverse. We'll switch our x and our y. We'll start by squaring both sides. And then add the 3 over. So we got x squared plus 3 is equal to y, and then I'll make that y in inverse. So our points we had before, we had 3, 0, which will now be 0, 3. We had we had 4. We had 4, 1, which will now be 1, 4. 7, 2, which is 2, 7, and 12, 3, which is 3, 12. So what I want you to do now is see if you can figure out what should those derivative values be just by your conjectures that you've made before. And then we'll actually check it by doing the actual derivative. So don't actually take the derivative and sub in. See if you can do it just based on the conjectures you made and working off of our slopes from the original. Okay, so hopefully you have something. Our derivative of this inverse would have just been 2x. So 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. So hopefully some of you got those without having to do the derivative. So our rule is if we have a point AB on F, then, now the notation for this is a little bit clunky. F inverse prime of B is equal to what? So you got a point AB on the original F. In your inverse, if you take the derivative at B, now the reason we're using B is because although B was a Y value in the original, B is where the X value is in the inverse. That's why we're doing it at B. So see if you can, either on your own or with someone around you, come up with what should that equal? And we should get that it's 1 over F prime of A. So if you're taking a derivative of an inverse at an original Y value, which is now the X value in the inverse, its derivative should equal 1 over the derivative at its corresponding value of X in that original derivative. Well, and if you're doing 1 over, that's essentially the reciprocal. So if we go to our white notes packets now, and we'll be in that the rest of the video. I want to go to one where it says exit ticket to start out. And this is not going to be the end of the video, because a couple more things we'll talk about. Now remember what we just said. We said if we have AB on F, then F inverse prime of B should equal 1 over F prime of A. So f of x is monotonic. We're going to talk about that in a second, but monotonic means either always increasing or always decreasing. The slope of f of x at PQ is 3. So really what we know from that is that f prime of P is equal to 3. Then we want to know which of the following is true. So we'll give you a minute, see if you or with people around you can figure out which choice would be correct. So this, what we have here, that essentially goes there. So we're looking for the inverse's derivative, or in other words, the slope of the inverse, which they all have. We need it at the original y value. So for us, that's at q. That rules out a and b. So we should just have 1 over 3. So that's choice C. So to make sure we've got it down, here's an additional example. You can just add on to the bottom of that page there. You don't have to write out the question, just your work. But what we're going to do, we're going to pause the video for 1 minute and see if you can answer that one. So this is essentially telling us that f prime of n is equal to 2/3. So we want f inverse prime at m, that should equal 1 over that 2/3, or in other words, 3/2. And that's the main thing with inverses that comes up on the AP exam. So just to close out the video, we're going to flip back some pages in the notes packet and just talk about a few key things. So if you flip back a few pages to where it says properties of inverses, and we're going to start down just a little bit below that. So just a reminder that f of x and f inverse, they're symmetric about the line y equals x. So that's what you would notice graphically. If f of x increases, then f inverse will also increase. And likewise, if f of x decreases, f inverse will also decrease. And we didn't end up graphing them, but if you wanted to go back to those examples we did in class and graph the original and graph the inverse, you would notice that they are consistent in that point. Moving down to the bottom, in the box there, an inverse only exists if f of x is 1 to 1. So what that means is x's and y's don't repeat. If x is repeated, we wouldn't have a function even to begin with. If y's repeat, then when you switch it to an inverse, then you'd have repeating x's, and then that's not a function. So 1 to 1, you can tell visually if it's passing both the vertical and horizontal line test in the original. If we go to the next page, there's our graph of sine x. So our domain of sine x is all real numbers. It goes on forever. The range of f of x is it stays between -1 and 1, inclusive. Well, notice you've got no x's repeating in that original, but the y's, they are repeating. That's not passing the horizontal line test. So sine inverse, its graph needs to be restricted. And we're going to do a whole bunch of stuff about the inverse trig functions on day 12 of this unit, but just a little thing about it. So our inverse, we just call sine inverse x. That can also be written as arctan x, or sorry, arcsine x. But as you see in the domain graph there, we're just going from -1 to 1, which that shouldn't be a huge surprise because that's just what the range was in the other one. Where the bigger surprise is in our new range, which should come from the domain. And what it is we need a branch that looks at all the possible outcomes of sine, all the way from -1 to 1. So for inverse sine, this just goes from -π/2 to π/2. And that ensures that the inverse is, in fact, a function. And we'll talk about on day 12 a little bit more of why it is that interval and not some other interval. And then down on the bottom, that's the last thing we'll look at in this video. So f of x is monotonic if it's always increasing or always decreasing. If it's always increasing or always decreasing, then we're guaranteed to be 1 to 1 because it's going to pass both the vertical and horizontal line tests. So if you're monotonic, since you're 1 to 1, that means that you would have an inverse. So if we want to prove something's monotonic, that means that we need to show either it's always increasing or always decreasing. Now, when we say always increasing or always decreasing, it could have a slope of 0 just for an instant, but it can't switch from like a decrease to an increase or vice versa. So to tell if something's increasing or decreasing, we would want to look at the derivative. So this would be 1/3 times 1 minus x to the -2/3. And by chain rule, we'd have to multiply by -1. And if we neaten that up, that's really -1 over 3 cubed root 1 minus x squared. Well, our critical values, that is never 0, but it will not exist at x equals 1. So on our number line, we'd have to put 1. We'd have our dy dx, and we would have x. Something left of there is 0. When you put 0 in for x in our derivative, we're going to get a negative over a positive, which is a negative. If you put, say, 2 in for x, you're going to have a negative, but then it's going to get squared. So in the end, that denominator will all be positive. Negative divided by a positive is a negative. So we can say, since let's say first, y always decreases since dy dx is never positive. Therefore, it is monotonic. Actually, let's not say it. Let's say y. Therefore, y is monotonic. And has an inverse. And I should specify that it's only okay for the derivative to be 0 for an instant. If the derivative was 0, say, for like an extended period of time, like there's a horizontal section of the graph, then that's a problem because that one passed the horizontal line test. But as long as it's only 0 for an instant, that's okay. All right, that's it for this video. Remember, the day 6 homework is due 2 class periods from now. Have a great rest of your day.